All right, so now let's take a look here at example number 3. It's kind of the same basic idea, and I'm going to ask you to maybe try to pause this video from time to time again to try to practice using some of this on your own. But here's the goal here. I want to set up but not evaluate an iterated integral in rectangular coordinates and in the specified order that's given, which will yield the volume of the solid, which is bounded by this quadric surface and the plane y equals 4. Okay, notice here in part A, I have kind of an added difficulty of I want to set up the iterated integral specifically so the differentials are in this order. And that seems very, very difficult maybe at the start, but we might be able to figure out how to make this work. Okay, let's see what we got. This is kind of a very, very interesting sort of a surface, and that might be the first step. So again, I'll start here by saying we draw a picture of the solid E. All right, so let's see here. I have a y equals stuff with x's and z's. I might be able to get a sense very, very quickly, though, of what this quadric surface looks like, because if I stare down the x-axis, I see a parabola. If I stare down the z-axis, I still see a parabola. And if I stare down the y-axis, I see something like a circle. So staring down the y-axis, I see a bunch of different circles. I'm going to go ahead and draw a picture then of what this might possibly begin to look like. So let's just imagine that I have circles kind of staring down the y-axis, kind of like this. And then I have these parabola-like shapes kind of occurring in these other directions. So maybe I have something that kind of looks something like this, right? And maybe, again, this looks like this would kind of go through here, maybe popping out there. So there's my x, my y, and my z. And I can see that where I'm stopping over here at the edge is at y coordinate 4. Okay. So I kind of have this sort of a shape in here. I guess this is trying to be slightly angled so it acts as an edge. Right, so I have something kind of like this solid sitting over here at the side. And I want to find the volume of it. Now remember, a triple integral is not built to find us volume by itself. That's what the double integral was supposed to do. But remember, there is a way that I can easily determine the volume. Think about, again, what am I going to have to integrate? Not what are the bounds, but what function do I integrate? Again, the answer should be, I want to integrate the function 1. I just have to find the bounds on this solid first. So I'm going to go ahead and think about ways that I can begin to communicate E. This solid E is built of a bunch of points, x, y's, z's. And I can already see a couple properties that are true about this solid. All the points that I need to use need to have a y coordinate that's less than or equal to 4. That's got to be the case. But again, I can kind of imagine maybe a little person standing on the inside or floating around on the inside of that particular solid. If they can bump into this side over here, this circular side at 4, how far back can they go? What do they bump into on the back edge? Well, what you might be able to see is they're going to bump into like this wall, right? Like whatever they, depending on how high or low they are, they're going to kind of hit that edge. So I can also say that my y has to be greater than or equal to x squared plus z squared. Okay. So I have to have something like this be true. Notice that what I'm doing right at the beginning is I'm starting to bound y at the beginning, which is good news because I'd like to bound y because that's the first thing I'm interested in actually working with. So notice here that when I say I want y to be wedged between two functions, I kind of already have it. Y is wedged between these two functions. Well, that makes things super, super easy because now that y is wedged between these two functions, I need to go ahead and do the following. I'll say we will now project the solid into the xz plane. Again, I need to try to think about how much space do I actually have to kind of walk around in. And I can see that by imagining if I could take this picture and rotate it so I could look at it just from the X and Z plane. That is, if you kind of imagine taking this entire picture and like squishing it down or looking at it from only the direction of the green arrows, what is the picture that I would see? What is the shadow that gets cast back in the XZ plane? And what I might see is that, well, wouldn't I really only see this big circle? Like, wouldn't that kind of just get put right back here? Right? Like, there's the shadow that's getting cast. And so that ends up being my projection. I can see that that's a circle when y is at a 4. And if y is at a 4, then I can easily see what that circle is. Okay? So I can see here that we have a circle of radius 2. Since we have 4 is equal to x squared plus z squared. That's, again, the formula that would correspond to this kind of cap on our solid there. Okay. So again, this is kind of strange because we're not dealing with a floor and ceiling here, but we're kind of dealing with like a front and back at the start. No big deal. We want to go ahead and actually try to take a look at this. I want to go ahead and think about how I could define D and how I could draw it. So I'm going to draw here an X and a Z coordinate system. I'm going to sketch out my circle, which has radius 2. Okay, if I want to go ahead and define this now in the order, or integrate now in the order with dz then dx, then that means that when I define this region D, this is a bunch of x comma z points, and I want z to be bounded by functions. So I can think about what functions could actually bound z. Now, that's actually not too tough because I could maybe imagine that I could use like the top half of the circle and the bottom half of the circle as different functions. Can you think of a way I could come up with equations for the top half and the bottom half of that circle? Well, one obvious choice is that I could go ahead and start to work with the equation that I've been given. I could see that I could get a negative 4 minus an x squared, and positive root 4 minus an x squared as bounds on z. And then my bounds on x, where would x range from? X should range from negative 2 to 2. So this kind of communicates the exact circle that I have here. And again, I wanted to bound z by functions because that's my second differential, and my very last one has to be dealing with constants. So the volume, when I integrate over E, I'm interested in integrating 1 so I can get the volume, and that corresponds to the following triple integral. We're going to integrate dy, dz, dx, and I just put on my appropriate bounds. Now, this can get a little bit cumbersome because you're going to have these really nasty looking bounds sometimes in the top and the bottom. That might require that you space out your integrals and really think carefully about which bounds you're working with every time you attempt to integrate, because you can see how cluttered this can get. But this does indeed wrap up part A. If you take a look at part B, you'll see that the same question is kind of still in play. We just want to go ahead and reverse some of the bounds that we're going to attempt to use. So we want to go ahead and say, well, wait a minute, what if I wanted to integrate with respect to z first? What if instead of looking at that solid and imagining kind of like a front and a back, what if I imagined again a floor and a ceiling? That's integrating with respect to z first. Then how does that change the problem? Well, fortunately, that's not too terrible to try to go ahead and figure out, and we can actually go ahead and work with that pretty simply. Okay. I'm going to go ahead and take a look here to see how exactly I could start to reverse this. So again, we know that E was given as a whole bunch of x comma y comma z points, where y was going to be less than or equal to 4, but y was also going to be greater than or equal to x squared plus z squared. Okay. Now, if I'm interested in starting by bounding z, I could start to think, well, I really only have one inequality that works with z. So if y has to be greater than or equal to x squared plus z squared, and I start to manipulate this, that should automatically give me that z squared is less than or equal to y squared minus x squared. Notice I just kind of moved the x squared to the other side, flip the inequality. If I square root both sides, I have to be a little bit careful. The square rooting of both sides is going to produce an absolute value of z on one side and the square root on the other side. But if the absolute value is less than or equal to something, that gives me that z is actually bounded between the positive and the negative of these values. This is all just some algebra sorts of skills that you've probably seen many times before. Okay. Notice though, I was able to bound z, and if z is bounded first, I could now think about, if I already now have a floor and a ceiling, I've kind of identified how low and how high I can go, kind of like these two blue pieces here. I could now think about what's the projection into the xy plane. That would be changing my arrows here to be imagining if I was looking down, what shape would I see? All right, so let's see. We will project E into the xy plane. Notice I'm using always whatever variables I didn't bound originally. Okay, if I was to look down on top of this thing and I want to see like the footprint, the shadow again that gets cast, can you start to think about what shadow you might see below this? Well, one answer might be I might see a shadow like this shadow here in red. I might see something that looks like this, but maybe also jutting out on the other side. Like I might have this parabola-like shape sitting down there. So I'm going to have a picture that maybe looks something like this. I could see that in the xy plane, y goes up to 4, and I have this parabola-like shape all the way up until that point. This again right here is my region D. I can then, of course, see that if I was in the xy plane, my original formula, which was y equals x squared plus z squared, would just be simplified to y equals x squared, because z is 0. But now I have a region, and I can easily start to work through and think about, do I imagine this region with a top-bottom or a left-right? Well, if I want to go ahead and put bounds on y first, I kind of have to imagine this with a top-bottom. So I can see here that D is a bunch of x comma y points. What's the lowest y can get to if I'm in that region? Well, it should be x squared. What's the biggest it can get to? It should be 4. And of course, my bounds on x are pretty darn free. They still go from -2 to 2, since those would be the values that I could plug in to produce that y coordinate of 4. Now that I have this, I'm ready to set up the triple integral. See if you can go ahead and actually set it up here on your own and compare with my answer in just a moment. All right, so here's my answer that I'm coming up with. Z again is my innermost integral. Then I have my y, and then I have my x. So notice I'm going to replace that dv with my dz, dy, dx. So we should be comfortable with kind of changing the order of those differentials at the back and recognize that it's not just a quick switch. I can't just interchange the values. I have to actually completely rethink through the region. All right, we'll take a look at example number 4, the last example for this section, in the next video.